There you go. Back of your head's not enough. They would make it better, but you're not. Okay. These are a small number of reactions, and these are generic reactions, which means for every one of these reactions, you could have a whole bunch of other ones that might look different to you, and hopefully at some point don't look different. So we'll talk about what these are in a minute. We have three different definitions we're going to be working with acid-base, and it depends on what we're talking about. We're going to be working with one main one called Bronsted and Lowry, and we'll deal with that later. And then we'll talk about ones with Lewis. Now, often in chemistry they're like, how do you know which one to use? How do you know which equation to use? And the answer is usually don't tell you. So like, according to Lewis, why is this an acid? And so you follow by Lewis acid definitions and say it does this. And you're like, that's why it's Lewis acid. If they say, why is this a Bronsted acid? And you describe why it's a Lewis acid, that's the wrong answer. So it will flat out tell you how to answer it. To answer these kind of questions, we need to know definitions. We need to understand the function of these definitions, not just memorize words in the scene. But at the very beginning, all the acid-base stuff we deal with are aqueous. So it's all about water. And in fact, the whole pH scale is water-based scale. So first of all, let's see what water is. Kind of like first day biology freshman year. We'll look at it from a different point of view. They looked at it from it's bent and polar and all that kind of stuff. We're going to look at it as water's made of two things. And it's a hydrogen ion and it's a hydroxide ion. These are the two things that water is made of. I would hate for that to go through the whole time ago. All right, I got to start over again. Sorry, it's been an hour now. And then the crazy part is the simplest thing is also all this stuff functions by opposites attract. What do you think the hydrogen ion is going to be attracted to?
Hydroxide.
Something negative. And guess what the hydroxide will be attracted to? There you go. Now you know acid base. We're kind of all done now. Everything else is just downhill. So we're going to talk about some things that are negative. You tell me if you recognize any of these things. Chloride, bromide, iodide, nitrate, sulfate, perchlorate. What do these all have in common?
Negative ions.
They're negative ions. They're anions. The first several are halides, right? Not halogens, but halides because they're the ion version of it, so that's well done. And the other ones are polyatomic ions. Which one is, you can argue several things, which one's completely different than the other five?
Perchlorate?
Sulfate,
Oh, because it's 2 minutes.
because it's 2 mites. If I put a hydrogen in front of these, I have an acid, and my generic acid is a Ha. And Ha doesn't stand for hydrogen and acid. Hydrogen stands for a hydrogen ion and an anion. You agree that all these are anions?
Yeah.
So if I put an H plus in front of these, I have an acid. How many H pluses would I need to put in front of sulfate?
2.
2, because we're going to crisscross like ionic compounds. If I ask you if they're ionic, you're going to tell me no, these are molecules. But in water, they fall apart into ions like ionic compounds do. Do you remember that if you put French fry salt, NaCl, into water, you don't have NaCl anymore?
Yes.
You have Na plus, and separately, you have Cl minus. You put one thing into water, and you have two things. If you said they would attach, and they may or may not attach, what would the Na plus attach to in water?
The OH.
The OH. If it did, that's what it would attach to. And what would the Cl minus attach to?
The H.
The H plus, because it's opposites attract, and this is how things function. So if I put HCl, HBr, HI, HNO3, H2SO4, and HClO4, these are all versions of one kind of acid that I call Ha's. These are the 6 strong acids. Not 6 strong acids, the 6 strong acids. Which means every other acid is what?
Weak.
Weak. Every other one is weak. How do you know it's a weak acid?
Not one of those 6.
It's not one of the 6. Would you rather memorize 6 or all the hundreds other ones? And you're like, just memorize the 6. Which halogens or which halides are shown in the 6 strong acids? As in, just by themselves, halides.
Fluorine.
Which one's missing, I should say, I guess.
Fluorine.
Fluorine. So if you had HF, I write down HF, would you say this is an acid?
It's weak.
It's an acid.
It's a weak acid.
Yes, it's an acid because it's an H plus, and we'll describe it by definitions in a minute. But if I say is it strong, you'll say no, it's weak. So we need to define what weak is and strong is. So strong for acids and bases, strong means 100% ionized, which means how much of it falls into ions?
100%.
All of it, right? Or you could say, this is an or, not an and, or 100% dissociates. Not disassociates, but dissociates. Dissociates means what?
Like,
Separate.
goes separate.
Yeah, they just separate. I have a pin with a cap on it, and then I move this, and now I have a pin and a cap.
Dissociates.
Except for the fact they're farther away, how did they change?
Wait, what? They said
Two.
Except for the fact that they're farther away, how did they change?
Oh.
They didn't. This is the cap, this is the pin, this is a pin and a cap. Used a lot. Thank you.
Thank you, Mr. Pitch. Have a good day.
So this is an H plus, this is a Cl minus. You move it away from each other and you got an H plus and a Cl minus. How's that different? The answer is it's just separate. So dissociate means they separate. Would you be okay in the fact that this is a salt?
Yeah.
This is the salt also, French fry salt? And this is an ionic compound, which means it's made of what?
Ion.
Ions. So the S is an Na plus
Yeah.
and the Cl minus already.
Yeah.
And so when I separate them, and it separates to an Na plus and a Cl minus, they're exactly the same except they just moved away. This is not redox, it's not a big time chemical reaction, they just moved away. Acids will just move away from each other, and therefore, this is what dissociation means. Weak ones don't 100% dissociate. Please don't say 100, the strong ones 100% dissociate, weak ones don't. Because don't would include don't dissociate at all, which that's not true. Also, think about this in terms of your test grade. If you don't make 100, you're disappointed. Does it matter what grade you make after that if you don't make 100?
Yes.
Yes, it absolutely does. Like, I made a 95, you made a 25. Doesn't matter, we neither of us made 100. Like, no, there's a big difference between 95 and 25. Not 100 though, like, no, it's not 100, but big difference. So there's stronger weak ones and there's weaker weak ones, but the weak is defined as not 100%. And actually, when they are weak, it's like bombing a test. Like you're making a 5, literally. So most weak acids dissociate less than 5%. So not only is it not 100, it's way down here. And sometimes it could be a percent, it could be like 10 different percent, sometimes it could be really, really low. So there's different ranges within the range of weak acids and weak bases. All right. This is one kind of acid. The other kind of acid is a choo-choo. You got Haas and choo-choos. You know what a choo-choo is?
Train.
Yes, it's a train. You know what this choo-choo is?
Carbon,
Carbon.
oxygen,
It's a
hydroxide.
carboxylic acid. This is a carboxylic acid. This is an organic acid. And while that is a structural view of it, it doesn't do a good job of showing structure, but everybody knows what it looks like. And what it looks like is a carbon that has a double bonded oxygen, a single bonded oxygen, and technically this thing is bent like water and polar. What had happened was the oxygens are very electronegative. They're second place next to fluorine. They pull the shared pair toward them. If I went to the bottom of my pool and dug a hole, what would happen really fast?
The water.
The water would fill in the hole, right? So this oxygen will pull the electrons toward it. It will siphon the electrons toward it, making a hole, an electron deficient hole. And therefore, electrons will flow into this hole. If this guy's getting electrons pulled toward it, and he's already pulled electrons, he really pulls the electrons toward it, making this bond very weak. And with the weak bond, guess what the hydrogen does?
Breaks.
Breaks off as a hydrogen ion, and the pair of electrons stay with the choo-choo, making it into a COO minus. Guess what a COO minus is?
C double
Starts with an A.
An acid.
It's an anion. So you can kind of think of organic acids are, how's it backwards? It's an H plus at the end, and then the COO becomes a minus, that's the anion. So it looks really different, but it kind of functions the same way. It's going to have a hydrogen ion fall off. And what part of the choo-choo falls off? The caboose. Do you ever know what a caboose is?
Yeah.
The leader,
Yeah.
or the end.
You know why they had cabooses before?
Because they had to make sure no one got lost. What?
No. So what happened is people who like worked on the train would stay on the train, like work their whole like whatever week, and so that was their living quarters was in the caboose. And then nowadays, the people are like, I'm not doing that, and they get an Uber and go to a hotel and stay somewhere, right? That's what they do. They get put up by the train company and everything, but they used to live in the caboose.
She's probably stupid.
So that's why they had a caboose.
She just got this.
No, I didn't. No, I didn't.
Because she
I-
thought.
No, she thought you were referencing the caboose, like how in kindergarten we have the lines, and
Oh.
somebody picked to be the caboose.
I thought you were talking about like a big booty or something like that. Just kidding. We're not. Unsubscribe, please. That was, never mind.
Listen to Christian music.
Okay, so we know this is an acid by recognition. Choo-choo, this is an acid. Is it strong or weak?
Weak, very weak.
All organic acids are weak because none of these are organic. These are all Haas. These are inorganic. By the way, these three, and this is not a big time test question, but just in case terminology confuses you, these are called oxyacids. Guess why?
Because
They have oxygen.
They have oxygen, but that's not really why. The reason why is the hydrogens are actually attached to the oxygens. They're not attached to the actual halogen or the non-metal. Or the other non-metals. They're actually attached to the oxygens on the outside of said non-metal, like chlorine or sulfur or nitrogen. Yes.
The three strong acids on the right, those are oxalic or
Those are called
they
oxyacids
have the oxygen.
because they have the oxygens. That's how you can tell. And the hydrogen's actually attached to the oxygen. It's not attached to the sulfur or the nitrogen or chlorine or whatever else I have up there.
Thank you.
You're welcome. Also, something you might recognize in here in terms of like the 8-night version of things and the hypo and ite and the 8 and the per 8. How are these related? Of the ones you've learned.
So we also have negative one charge.
The oxy ones? Are you talking about the oxy ones?
Just these three oxy ones. How are these three oxy ones related?
Are they all-
Besides the fact they're oxy.
They're, yeah.
They're all polyatomic ions. Like within the polyatomic ions, how are they related?
Sulfuric acid.
They're the ones that you've learned in each category that has the most oxygen.
Yeah. Oh.
So you learned nitrite and nitrate, and this is the nitrate. You learned sulfite and sulfate, and this is the sulfate.
And peroxide.
You learned perite, ite, 8, and hypo-8, and this is the one with the most oxygens. So if I gave you two of these that had the same elements, you can't compare between these sets, but if I gave you like HClO2 and HClO, the one with more oxygen will be stronger.
Because oxygens are greedy.
Because it basically siphons more electrons, making a bigger hole and a bigger deficit in that bond. So the hard part to understand is the stronger the acid, the weaker the bond. Because the strong acids is when the hydrogen ions fall off completely. Why would they fall off completely? Because
they're
the bond is not very strong.
because they need to dissociate.
Well, yeah, they will dissociate because the bond is weak. If the bond was strong, it wouldn't want to fall apart. Okay, so we can recognize the two kinds of acids you'll get.
Yeah.
And I mean the normal two. We have others that we can recognize. And you can list all the strong acids, right? Or at least with your notes at this point. Maybe not memorize it, but with your notes you can list them. Bases. We have two kinds of bases. We have moos, and boring, we have amines and amines. This would be good if you had some organic, but we got some. No. A moo is going to be a metal hydroxide.
Is
Mu is a metal hydroxide. It doesn't have to be a group 1 metal, but we'll get to that later. A metal hydroxide contains its own hydroxide. You put it in the water, it will dissolve, it will dissociate into the aqueous metal ion and the hydroxide ion. This is called an Arrhenius base.
Arrhenius equation.
Same dude. Can't imagine two people have the same last name that did stuff in chemistry.
That was a niche pool.
You get a lot of
No, of course
quizzable questions on Arrhenius equation.
So yeah.
I went to a tournament this weekend and we got 2 or 3 and I got everyone. It was real. It asked. I got everyone.
Good.
It was a weird question.
But they thought you were really smart.
I mean, yeah, but Sachin was also there, so it was the bonus. It was awful for me.
I mean, you just covered it though, so
Yeah.
it's been a while since you covered it. Okay, so Arrhenius base, by definition, this means something that produces hydroxide ions. So Arrhenius base produces hydroxide ions. What do you think Arrhenius acid is?
Boom.
Metal plus acid.
No. Just by definition. First of all, do you agree that like acids and base you think of being like opposites?
Yeah.
Yeah.
Metals and non-metals you think of being opposites?
Yeah.
It kind of goes like that with definitions and with what's an acid, what's a base. They kind of go in opposites and they work really well. So if a Arrhenius base is something that produces a hydroxide ion, what do you think an Arrhenius acid is? Could be used as one, but it's not. Produces a hydrogen ion. So you put an acid in the water, and it shifts to the right, and it produces an H+. We're going to talk about Bronsted and Lowry acids and bases. Bronsted and Lowry is 2 guys, and this seldom happens anywhere in the world, much less in science. 2 guys independently came up with the same concept, and they both get credit. Usually somebody gets shafted.
Cough, cough.
There's another guy that came up with the periodic table at the same time Mendeleev did. You know what his name is?
Nope.
I don't either. He didn't market it very well. Literally, Mendeleev marketed the periodic table and the usefulness of having this organization, and so everybody that studies chemistry learns that Mendeleev came up with it, and the other guy's like, not a good marketer.
It's like Newton and the guy who did integration.
So when we talk about Arrhenius bases, an Arrhenius base is going to be a mu.
Nice one, Harry.
When we talk about Bronsted bases, they're going to be different. However, an Arrhenius acid and a Bronsted acid will be the same species, but by definition, it'll be different. So in terms of why it functions as a Bronsted base or Bronsted acid, you have to use the definition of it. Also, small things. Arrows to the right mean strong. If it's weak, it's got a double arrow. What does double arrow mean to you? Equilibrium. If we have an equilibrium, can we write an equal expression? If we have an equal expression, that equal expression will equal to K, a constant, which will never change unless we change temperature. So unless otherwise specified, all this chemistry will be at 25 degrees Celsius. And therefore you can look up K values and they're going to be constant. So it's at 25 degrees Celsius, which is probably a tad bit warm for us. I think we like 22 or so in America, but whatever.
It's 25.
It's 25 is officially standard reaction conditions, and so this will all be done at 25 degrees Celsius. You don't have to ask. The only way it'll be different is if they say, hey, I changed the temperature and it shifted this way, what's the new K value, stuff like that. Okay, how good are you with electron dots?
Pretty good.
Pretty good? This is like,
Jeeves in your book.
this is such an important thing to know, is this. Like so much, no pun intended, is based off this. Okay, so we okay with this thing is trigonal pyramidal.
Heck yeah. Yes.
It looks like the nitrogen, you got this guy, you got a wedge coming out, and a hash ring, you got things down here, and up here, you have a lone pair sticking out in space. Which means that lone pair, this is an asymmetric arrangement. The dipole moments do not cancel, and this is a polar molecule with a definite, strong, negative end to it.
Oh.
If I put H's down here, I have this thing called ammonia,
Yeah. Which is
and it's a base. The reason why you know it's a base is because I'm telling you it's a base. Ammonia is a base. Anything with a nitrogen in it is going to be a base. All the nitrogen guys we deal with are going to have 3 single bonds. Could they be different? Yes. You could have a triple bond, you could have a double and a single, but they're going to have 3 sticks. Every one you get in this chapter will have 3 single bonds. What else could we put on the nitrogen other than hydrogens?
Oxygen.
Oxygen.
Hydrocarbons.
You'll say that.
Hydrocarbons. So back in the day, we would call a generic hydrocarbon an R group. So if we had CH3NH2, how many things are attached to the nitrogen here?
3.
3. You got 2 hydrogens and what we call a methyl group. What does meth mean? One carbon. One carbon. And there's a difference between one branch of 2 and 2 branches of 1. So 2 branches of 1 is called dimethyl. 1 branch of 2 is called ethyl. Right, here's a carbon that's separate. So those are 2 branches of 1, those are dimethyl. Here's a carbon stuck to another carbon, is one longer branch, that's the ethyl group. Remember this? What's a branch of 3? Propyl. A branch of 4? Butyl. Not that we'd have a branch bigger than that, but then it goes like normal stuff like pent, hex, het, oct, non, and dec, as in decane. Oct is in octane. You guys ever heard of octane?
Yes.
You ever like pump gas? Just me. I'm the only one that doesn't have a battery operated car. Okay. So you pump gas and it has an octane rating on there. It says like 87, 89, 92, and it gets more expensive as you go up. If you have a performance gas car, you gotta buy the expensive stuff. It's great. Super awesome. We okay with this? This is a base. This is a base. This is an amine. Any kind of nitrogen-based thing will be a base, and it's because of structure. I really want you to learn the structure. I will refer back to this over and over and over and over again. This is trigonal pyramidal, is bent and highly polar and highly negative end. And what do negative ends hook up with?
Positive.
Positive. What's positive in water?
H plus.
H plus. So the H plus will stick to it. What's left over?
The OH.
The OH, which makes it a base. This is not going to be an Arrhenius base, however. This will be a Bronsted base. So we're going to have index 3, and the generic one is going to be B for base. This is going to be an organic base. This is an amine or an ammonia, some kind of nitrogen base, my generic one. For Bronsted, you have to have 2 things on the left and 2 things on the right. And usually what you have on the left is water and something else. Water's made of what 2 things? Hydrogen ion and a hydroxide ion, right? It's not made of hydrogens and oxygen. It's made of a plus thing and a minus thing. What do we know about the polarity of the nitrogen? Polar, and what's charged on the nitrogen? Negative. So what we're going to do is we're going to grab the H plus and transfer it. And when you break off the H and the plus and you put the H and the plus on here, this is called adding. What do you have if you have 0 and you add 1? 1. What if you have 0 and you lose 1? Good. What if you have 3 hydrogens and you gain a hydrogen? 4. So we're going to have H4 plus and OH minus. You got to balance the charges as well as count the hydrogens correctly. This is not something fancy. We're literally moving an H plus. And Bronsted Lowry, which we call Bronsted because we're too lazy to give the other guy credit. I mean, he's from England anyway. They got enough.
They don't matter.
Bronsted Danish. They don't. I mean, how many Danish?
They stole too much.
I do like Danishes though. They're tasty.
Do we have to remember that name?
Yes.
Can you write it out?
Bronsted. BRON. STED.
So this is Bronsted.
This is Bronsted underneath the line. The top 2 are Arrhenius. The bottom 2 are going to be Bronsted. So, definition. Also, before I get back to that, just segue. What's a hydrogen made of? A typical, ordinary If you got 99 of them, what would be made of? Besides I know it's protons, neutrons, electrons. How many of each?
1 proton, 0 neutrons, 1 electron.
Okay, 0 neutrons, because the whole thing weighs 1 on average, and these weigh 1, so on average there's no neutrons, right? So how do you make something into a positive ion?
You add an electron.
You
Take away.
take away an electron. So I had 1, so how many do I have now?
0.
So what is an H plus?
2 protons.
It's one, it's just proton.
I thought it was
proton.
added.
No, we took away an electron. Literally, an H plus is a proton.
Crazy.
Okay, so this is going to be a proton receiver. As many people that I teach that want to go to these schools that rhyme with Harvard and Bale, they can't spell receive. And it follows the exception rule, and that is I before E,
Except after
except after C. And this is after C, so please write it R-E-C-E-I-V-E.
Am I gonna go to Will you count off if you?
Just for the hell of it, yes.
Am I gonna go to Harvard?
Please unsubscribe.
Am I gonna go to Harvard? Because
You
I
want- you
know
get
to
Bar-
spell it.
Yeah,
Can I go
you're going to drown.
I can go to drown.
You're going to drown.
You're gonna drown?
No.
No, not going to drown. She's going to get a drown.
Talia's always been.
So it's a proton receiver. Also, you can say a hydrogen ion receiver, same thing. So you don't have to say proton receiver. Just if they tell you proton receiver, I want you to understand the same thing as hydrogen ion receiver. If okay, the hydrogen ion and proton are exactly the same thing. Guess what a Bronsted acid is?
It's the one that is
It's a proton donor.
You can tell me
So this is the base, which means water is acting like an acid. Nobody likes you when you act like an acid, by the way.
Yeah.
So this is going to be a proton donor. And if you forget the term, just think like it's the proton giver-upper. You're going to get credit, right? There's no exact term for it. So it donates the proton, it gives up the proton, that kind of thing. Be okay with this?
Wait, so the acid is the receiver.
I'm picking up these.
Acid is the proton donor,
It's a
base is proton receiver. Also, can't this equation go both ways?
Yeah.
All right, so if we pretended like it shifted to the right, and therefore these are reactants for a while, even though we always call these products, going from right to left, do like a,
Thank you.
what is the ammonium ion doing going from right to left?
Receiving.
No, it's donating.
Right to left.
It's given. It's given.
It's
the
donor. Donor.
How is it?
It donates.
Yes.
It donates.
Because this will go off in here. Which, what does that make OH minus?
Receiver.
Receiver. The
And therefore?
receiver, the base.
If you write an equation and you write an H plus in there by itself, or you write an OH minus in there by itself, the H plus will always be the acid, the OH minus will always be the base. Guaranteed. Now this is producing a base, talking about going from left to right, but still the OH minus will be the base. It will never be the acid. And H plus, same thing. What is the difference between these two species? Not like in function, but like in actual like structure. What is the difference between these two?
One is an extra H plus ion.
Yes, they differ. They differ by an H plus, and these two also differ by an H plus.
Yeah. They're basically.
These are called conjugate pairs.
Conjugate.
What is the definition of a conjugate pair?
Opposite.
More specific. They are going to be opposite. They will be acid base, but that's not a definition. So if you list one, if you get these are conjugate pairs, and you know this guy's an acid, this one's got to be a base. Otherwise, it's not a conjugate pair. But definition is how they differ.
By proton.
So why are these conjugate pairs? Because they differ by one H plus. Now, they can't differ by two H pluses. Otherwise, they're not conjugate pairs. These aren't series of things. These are like right next to each other. So you okay with picking out the conjugate pairs? You notice that the two things on the left side are opposite in terms of acid base. The two things on the right side are opposite in terms of acid base. The two conjugate pairs, or one set of conjugate pairs, those are opposite, and the other set of conjugate pairs are also opposite Everywhere you group these things, they're gonna be acid base, acid base, acid base, acid base. And obviously the product side, it's a plus sign between the two. So you could have acid base, base acid, or you could have acid base, or you could have base acid, acid. Like, you know, they're plus signs. They don't have to sequence that way, but you will have an acid base on the left, an acid base on the right, things like this. This is Bronsted. Now, I'm writing this equation with a known base in water, and we have a Bronsted acid and base and a Bronsted acid and base. I'm gonna do the same thing with an acid, and we'll have a Bronsted acid and base, and Bronsted acid and base. And it functions by changing it, switching it by 1 H plus. If I give this, can I erase part of this at least?
Yeah.
Wait, what is the delta H plus?
They differ by, they're changing, the conjugate pairs.
okay.
Yeah, they're different by the H
I
plus.
thought it was like thermo delta H for a second. I was
No,
like,
delta is changing.
So you're gonna get flat.
It doesn't have to be that. I watch Formula One racing, and they'll talk about one lap versus the next, and they'll say, "What's my delta?" And they're talking about what's the difference in my lap times, and nothing to do with thermodynamics. So, what's your favorite weak acid?
Favorite week?
HF.
HF.
That's it. Okay, that's good. Fun thing about HF. Can you get it? Thank you.
What's the boardwalk?
Oh, if we write equal expressions, this is important to write down phases. Sam says yes. Yes. Why is it important to write down phases? We're dealing with equilibrium.
because you have to know what's not part of it.
Yeah, because aqueous stuff, which we'll have in here, will go into expressions. Liquids, which we have in here, don't. We don't probably have solids or gases, but phases are important to know. So there's this comedian called Stephen Wright. He kind of looked like and acted like a stoned Bob Ross, had a big brown fro, and he said, I had some powdered water, but I didn't know what to add. Like, what? Same guy who said he spilled spot remover on his dog and he disappeared. Because he had dogs on his spot. No? Okay.
Oh, I get it. I get it.
He also said somebody broke in his house the other day, stole everything, and replaced it with exact replicas.
Ah.
He was a weird
That's
dude.
smart.
So anyway, you can't have aqueous water. You can't have water that's dissolved into water. Now, this is how we gotta look at it. Looking at H, like, by the way, you don't know what water is gonna do. You gotta know what this is gonna do. This is the starting point. If you don't know what this is gonna do, you can't figure it out. But we know HF is. We know it's an acid because it's a hopper. And if you were writing this equation, we know it's a weak acid. How do we know it's a weak acid? It's not a strong. So therefore, we put a double arrow. If this was HCl, we put a single arrow going to the right. It goes to completion and doesn't come back. This is important to know. All right, so it goes that way. By definition, according to Bronsted, what will this acid do?
It will.
We have a tour. Who's going to talk?
Be a donate.
Who's going to talk?
Alex.
Clear.
But they're
Alex has to
living.
talk.
Wasn't it
There it
Oh
is.
yeah, yeah.
No,
no.
It's
You
It's
said
Alex and then
They
I
chose
was
me last
after
time.
that.
Oh, right.
So you're next?
Yes.
Okay, well they passed. Okay, sorry. So Bronsted acids do what?
They're donate.
Donate a hydrogen ion. What do you think they're going to donate it to?
To the base.
Well, yes, but to what
the
thing?
To water.
H.
To water.
To the only other thing we have. So if you got this thing and it donates and you have one other thing, it's going to go to that. So we're going to have this thing where it goes this way, and it's going to be an H plus. So what does the HF look like over here?
F.
F.
Whoa.
Well,
F
minus.
minus.
F minus.
Yeah.
It's going to be, if I'm putting phases, it's going to be aqueous. And the water's going to look like
H3O.
plus.
Plus.
Now,
is that aqueous as well?
Wait, why is it O
is.
plus?
Pardon?
Why is it O plus?
Because you're donating a hydrogen ion. So this is 0, and you add a plus 1.
Oh, okay.
So literally, what is 0 plus 1 is plus 1.
So it makes the
What is 0 minus 1? And the answer is minus 1. So the charges will change. People often don't do that, and it's completely wrong if you don't have the charges up. H3O plus, we are assuming it's synonymous, exactly the same as H plus, which is really weird. Because usually in chemistry, if it's the slide's a bit different, it's completely different. Do you know that water is bent and polar?
Yeah.
That it's got a big time negative in and these hydrogens are big time positives. Yep. And if you put an H plus into water, these are gonna hook up and bond.
And this-
And if it hooks up and bond, you're gonna have an H3O plus. You could even have an H5O2 2 plus. Or no, still 1 plus, excuse me. You'd have this thing attached to another water because it's a solid plus. And then these will break and you stick another one. Like you never actually have an H plus floating around by itself, but it's so much easier to think of it that way. So we need to know that this thing is called the hydronium ion. Mr. Page is making up words. Hydronium ion. And it is exactly the same as an H plus in terms of what it is, how it functions, things like this. We will need to have an H plus concentration to figure out pH. The molarity of the hydronium ion is the molarity of the H plus concentration. And so if we have the molarity of the hydronium ion, we can figure out pH. So, HF, acid or base?
Acid.
What does that make water without even thinking about it?
Wait.
Base.
Base.
Oh, oops.
I mean, it's a lot of things, but I'm thinking in terms of acid base. What does, you think of it this way, what does the hydrogen fluoride turn into? And I'm gonna say the fluoride,
Yeah.
which means it's the conjugate, what? Acid or base?
Acid.
Base.
So this is an acid and therefore this is a conjugate base.
Oh.
And this is a base and therefore this is a conjugate acid. And these are conjugate pairs and these are conjugate pairs. Really good multiple choice questions. Which are the conjugate pairs? And they like give you all sorts of combinations. And you just gotta know that conjugate pairs differ by an H plus.
So basically, like whatever is on the other side of the equation is like the conjugate of whatever that is. So like you would change.
Yeah, but you just can't say that the hydronium ion is the conjugate of the HF.
Yeah. Yeah.
Right? So you, and then they could ask you what makes them conjugate pairs, and the answer is they differ by an H plus. So like functioning by definitions, again, not just memorizing them, but understanding how this works. They can also give you, you have these things called diprotic. What does diprotic, you think mean?
2 protons.
2 protons. It means 2 ionizable hydrogens. So this thing can fall apart into an H plus and an HSO4 minus, and this can fall apart into, keep writing, sorry, an H plus and an SO3 2 minus. We'll talk about how this works, and you don't really get 2 for a needle, but we'll talk about it later. But true or false, these two are conjugate pairs. True, because
Because they're different by.
different by an H plus. True or false, these two are conjugate pairs.
True.
True. True or false, these two are conjugate pairs.
False.
False, because they don't differ by
One.
N or 1 H plus.
Different by two.
They differ by 2, and therefore we don't consider them to be anything, although we recognize it's this diprotic thing going down like this.
Yeah.
You said this is an acid.
Yeah.
You said this is a base.
Yeah.
So if I put that in the water, it would be an acid. If I put the other one in the water, it would be a base.
No, it's a
No.
base with the hydroxide.
Good question. Well, I've asked you that.
Don't acids? I don't know. I'll be real.
If I could get fluoride into water, just fluoride. If I could just put fluoride in water only. By the way, I said into water, so water.
Is it a blue side?
How would it work?
It would
The H.
it would kind of act like an acid because it's dissolved.
What is water made of?
H plus and OH.
H plus and OH minus. What would like to react with the fluoride?
H plus.
The H plus. So would you say that maybe we could have HF over here?
Yeah.
Because what is a plus 1 and a minus 1?
Zero.
Zeros, right? What's left?
OH minus.
OH minus. If you write something that you've never seen, never heard of, never seen anywhere, it's probably wrong.
Okay.
I got an H3O minus 2. Like, you ever seen that? Like, no, it's probably wrong. Now, what does it say about OH minuses?
They are always bases.
They're always bases, right? So if I put this in water, I will be producing OH minuses, which means the pH will be above 7.
Yeah.
This is the base, which makes this, A base.
A base, yeah, because
it's
that
that.
it
So
makes.
it is a base by Bronsted because it's a proton receiver. It is a base because the pH would go up. So if I ask you specifically about Bronsted, you would have to refer to a hydrogen ion receiver or a proton receiver. That's why it's a base. But if I say what would happen to the pH, it's either going to stay 7, it's going to be below 7, it's going to be above 7. You say it's going to go above 7 because it's actually going to act like a base, not just a definition of one. Because we start on this side, and it's going to shift to the right because we have nothing on the right, which means it's producing OH minuses, and therefore, there you go. I can write this guy 3 different ways. Aren't you happy about this? Since they're aqueous, don't we have water already?
Yeah.
Yeah, okay. So writing water as a reactant, it's not like I gotta put something extra in there for it to be present. So these all, even the top one, even though they have water in it, is still present. However, if water is written as a reactant, it's gonna change, otherwise it's not gonna be in there. These are all the same thing. It's different ways to skin this cat. I don't know why you would skin a cat this. I'm not a big cat fan, but I would never do that. Anyway, any thoughts on that? What are some possibilities? And most of the stuff is like how acids functions and also things like what's water made of and things like that. You might have a guess. These are all the same reaction, but they will be written different and they look different, but it's the same thing.
Well, it's because they're all aqueous, so they're all the same. Which
Tell me 1, 2, or 3 and tell me what to put for a product.
for 2 it would be NH3, just normal, right? And then plus H3O negative. No,
Think about the charge.
H3O positive.
Yep, perfect. This is the conjugate of a base. You okay with it? NH3 is a base.
Yeah.
Because I told you this. It's ammonia, which is the type of amine that's not organic. It's a base, which means the conjugate is always the opposite. We said over there it's a conjugate acid. So, according to Bronsted, how do acids function?
As donors.
Donors. So we're going to get this and make it a donor.
Yeah,
Also, why would this not be a receiver of a hydrogen ion?
because it already
So you can't
has.
give another one.
Because you got a positive and then you got a positive and you stick them together?
No, they were.
It would, yeah, not. But do you have a negative end on the water
Yeah.
that the
Yeah.
positive could flop off and hit
Yeah.
it? Great. So you literally break it off like Lego, move the one hydrogen, move the charge, and then you end up with this. By the way, I said this is exactly the same as what?
H plus.
H plus, and H pluses are always what?
Acid.
Acids. So if you're producing H3O plus or you're producing H plus, this is an acidic environment. If I put this in the water and only this in the water, it will be below something because this will act like an acid. By Bronsted, it does it by proton donor. In terms of pH, it's producing hydroxide or hydronium ions or hydrogen ions, and therefore the pH will drop. To what degree is all math? We're going to deal with that later. Okay, two other similar things, because it's all the same thing. It's all acid. These are all acid.
Would
acid.
be
What's the
NH3
difference
plus-
Do what?
The top one, would it be the NH3 plus H plus?
It would be.
Thanks.
And this would be written as Arrhenius. But in the end, I don't care. Like, in terms of acids, it doesn't matter if written as Arrhenius or written by Bronsted. Unless they say, write a Bronsted equation for this. Then you need to add water. These will be Bronsted. All right, well, this will be a Bronsted. Because of the product, this won't be a Bronsted. But this one's not a Bronsted. But in terms of making a equilibrium expression, it will be. How many things will we have on top if we make an expression with this?
2.
2. How many things on the bottom?
1.
1. How many things on top if we make an expression with this?
2.
2. How many on the bottom? Think carefully.
No, 1.
1. Because?
One's
H2
a
is a
liquid.
liquid.
So we would have the same thing for the most part,
Yeah.
except this one would be an H3O plus and this was an H plus. So that's completely different, right?
Well, no, because
Is it-
it's
are
Well, no, no,
H2.
because the H plus and the
It's H2O, which is
I said H plus and H3O are going to
the same.
so they're not completely different. In fact, they're Identical,
Completely the same.
even though they don't look identical. Yeah, completely the same. All right, the last one.
What's the difference? I can't tell.
Between the last two notes.
Yeah.
In this one, we're gonna do opposites attract.
Okay.
That's my hint.
So
So you need an OH minus.
And the OH minus because we're
On the
Yep.
like
What's the
with
H?
the what?
Oh, with the
We're by itself or like what are we
with
talking?
the N plus.
NH4 plus nope. NH4OH plus
Plus
uh,
H plus.
H plus. Okay, this is aqueous, this is aqueous, this is aqueous, this is aqueous. These squiggly things are aqueous. Water is always gonna be a liquid because you can't have powdered water and add something to it. So we have two things on top, one thing on the bottom, and one of the things on top is an H plus. Two things on top, one on the bottom. One of the things is a hydronium ion, which is the same as an H plus. And this would have two things on top and one thing on the bottom, and this top part would be H plus. If you wrote them any way here and did this math that we haven't talked about, it's all correct. It's all correct. So sometimes if you get stuck, you can figure it out. Have you seen these things before? And even, I don't know, have you even seen ammonium hydroxide before? I mean, it is an ionic compound that we would crisscross from days of nomenclature, so
Yeah.
maybe not.
I feel like we have.
So these two are actually going to be, well, this one is going to be Bronsted. This is not Bronsted because there's not a proton donor. It's a hydroxide ion donor. So it's not really a thing, but it works in terms of math. This is the Bronsted, this is Arrhenius. So if they say write it as Bronsted, you have to have water in it, and this has got to be a proton changing from one to the other. But if you just got to come up with an equation, any of these three will work.
What is the third one? It's Arrhenius Bronson.
This is not really a name. I don't even have a name for it. I mean, I guess it could be considered Arrhenius because this guy is actually producing the hydrogen ion and dropping it off. Whereas like when you have this guy and then you have water and we have NH4 plus the hydroxide, isn't this the base?
Yeah. Wait, no. Isn't that the ash?
Do you want to answer?
Ammonia, is this the base or not?
I thought it was the acid.
No, that's a
No, it's an acid.
Because
We have ammonia and we have ammonium. And
Wait, NH3 would be a
Is it
base.
nice?
no, it's an acid.
This is the base.
Base.
Base? Wait, what?
This is not the same,
Oh yeah, nitrogen is the
Oh.
base. I
right?
didn't remember that right.
Yeah,
This is not the same at all.
No.
No.
In fact, it's the opposite of the same. In fact, they're conjugates of each other, which means they're opposites. So this is a conjugate acid, and this is the base it came from. So okay, this is the base. Where did the hydroxide actually come from?
The H2O.
The water. So this is not Arrhenius because this guy is not actually producing the hydroxide. The reaction does produce hydroxide, but the hydroxide doesn't come from this, and therefore this is not Arrhenius. This is done by a transfer of a single H plus, and therefore this is a Bronsted reaction. That's the Bronsted base, acid, acid, base, because of donating or receiving a hydrogen ion. Be okay with this? This is where it gets like, this is the part that is the very center core, how things function, and this is really difficult. And there's so many different things that you get confused, but there's only a few generic things. So let's go back to this. What is this?
Arrhenius.
acid.
Acid.
An anion.
Yes, this is the conjugate
Conjugate.
of Ha. We can just think of conjugate meaning opposite, I guess.
Yeah.
Because if the HA is an acid, the conjugate would be a.
Base.
So if it actually functions in water as something, it would function as a base. What is a mu?
A base.
I wrote mu. It's a base.
Base. And then
What do you think the Ma plus is?
it's an acid.
It is an acid. By the way, what would a metal ion hook up with in water?
Wouldn't it hook up with OH?
It would hook up with a hydroxide ion, leaving you what?
Uh,
H
Uh,
plus.
H plus.
H
And if you are left with H pluses, This is an acidic environment. So by putting this in the water, it would form an acidic environment, and therefore this is an acid. Different kinds of acids. Be okay, this is an acid.
Yeah.
Yes.
Choo-choos are acids. This would be the conjugate of the acid and not the acid, and therefore this would act like a what?
A base.
Base.
A base.
Because it would take a hydrogen out of the water, making it a basic environment.
Wow.
I kind of just copy and pasted what you would say.
This is always the way.
It's always
It's
an
always
acid.
the acid.
Always an acid. And if you had this in water, it would be an acidic environment.
Yeah.
Now you gotta remember, if it's reacting, it's not in the environment, it's moving away. So you gotta be careful about where you see it. Hydroxide is always the base. And very, very tricky. Famous Run DMC. It's tricky, tricky.
Base.
It's one of two.
Base.
It's what happens when you beat somebody up.
Amphiteric.
So,
It's a salt. And a salt is made of
and
an acid
And a base.
and a base.
Amphiteric. Is that
Well, it's not gonna act like an acid
Yes, it is.
and a base. It's actually made up of two pieces. So this is my plus and this is my minus. And we said that a minus is a base, correct? And we said an H plus is an acid, correct?
Yeah.
So this is made of both things, and it really depends on what they're made of as to which one it actually functions by. But it is not made of one thing. These are all one thing, and you get down to here, and that's actually two things. You put a salt in the water, and it dissociates. You got Na plus. Also, the metal ion could also be the ammonium ion, because it could be a cation, which was a conjugate acid we already did with. The faster you can recognize these pieces is what they are, and I would start with ha's, moo's, choo-choos, and amines. Amines are going to be in HX, or it could be
Did you have a lockdown?
No, it's not. Just
Not a very good alarm. If we did have it.
Well, what's-
it's the alarm.
oh, I figure what we're talking.
weather.
It's like
Always trying to trick us. Right? Nobody's after you.
I was going to do this.
okay, cool, thanks. I was thinking they were them too. So.
The apocalypse.
Okay, if you have an amine, what is the shape of ammonia?
Ammonia is.
Oh, trigonal pyramid.
Trigonal pyramidal, and there's a big lone pair on the top. That big lone pair is going to be an orbital of electrons sticking out in space, and what is that charge of that orbital of electrons?
It's negative. so it
Negative.
attracts
So what do
base.
negatives hook up with?
Base.
Positive. What's positive in water? H plus. What does that lead you?
Oh,
Oh,
it's
minus.
Which means it's a basic solution.
Sweet.
I
Wow.
We go with this?
Yeah.
We go with this meaning you had time to write it down. Not that you're
Yeah.
proficient.
Got her down.
So the M plus A minus is just based off of what it's made out of?
Yeah, we gotta evaluate it.
Okay.
We will learn that some things don't do anything in water, so we have to be able to learn how to disregard them, which is confusing. I'm gonna switch to just water. Just water.
What?
I see my water is.
That's what you said.
H2O.
No. Water is so confused. What to do?
I wrote like an Arrhenius version of water and a Bronzite version of water. I like the Arrhenius version better. But write whatever you want to write, doesn't matter. And then if they say write a Bronsted version of something, you gotta do this. They usually don't ask for Bronsted for water, but they will ask for a Bronsted for a reaction, which means you need two things on the left, two things on the right, one of them's water. You okay with this thing just fell apart into the two pieces?
Yeah.
What do you think the phase is for water?
Liquid.
It's liquid. What about the phases for the other two?
Aqueous.
Aqueous. If I wanted to write an equilibrium expression for this, I'm going to write down K equals concentration H plus, concentration OH minus over 1. And since I want to know what kind of K this is, I'm going to put a little sticky note on here and call it KW. You give this,
Are we gonna have to calculate equilibrium in this?
yeah. But we'll know water, so this is a number you'll memorize. It's not complicated. Water by itself at 25 degrees Celsius with nothing in it will dissociate to 1/10 millionth of a molar. And of course, if it breaks in half, what is the concentration of the hydroxide ion?
It breaks in half, so it's half that.
Nope.
It still isn't.
It's square root.
We're not throwing pin tops at yours one time? Or maybe Talia or somebody, no? Okay, so I'm getting tired of Talia, so I'm throwing stuff at her, right? And so I need to throw more stuff, so I'm gonna take the tops off. If I have 50 pins, how many things can I throw at her?
100.
So I have 50 tops and 50 pins without tops? So no matter what I break in half, I have equal amount? Great, so I'm gonna break this water, no matter how much you break, it's equal amounts. Okay? However, these things can vary like crazy. What would happen if, according to Chatelier, what would happen if I put an acid into water? By the way, putting an acid into water means I'm putting a bunch of H pluses into water.
The concentration would get higher.
Concentration of H plus would get higher, and therefore it would shift.
To the
It would
left.
shift
Right,
to the
right.
left. To decrease the number.
Okay, I got a few votes over here. If I put acid in water, I'm adding a whole bunch of H pluses. It's gotta move in a way to do what? It's gonna go left. I gotta move in a way to reduce it. Now, if I put a whole bunch in here, I mean, how much does it take to be a whole bunch?
Well, however much.
Not much. This is 1/10 millionth of a molar. What if I put in like 1,000th of a molar?
Yeah, that's gonna.
If I put in 1,000th of a molar, I'll put in 10,000 times more. So when it shifts to the left, how much base could it use up? Less than this. How much of the hydrogen ion would you have? The same. Because if I use up all of this, and it won't, because that's what equilibriums do, and I added enough acid to be 1,000th of a molar, but I used up this much, how much do I have left? According to Sig Figs, I have this much left over. I don't have 0.000999999. According to Sig Figs, you look at the place values and it's like same amount because it's such a small amount. But that is what happens when it shifts. So, but we can do it, calculate mathematically. So if this is how much you have at room temperature, and therefore this is how much you have, then this will equal to 10 to the minus 14th. Because that times that is 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. And therefore, if this thing increases to 10 to the minus 3, what does the hydroxide ion have to decrease to?
10
to minus 10?
10 to the minus
10.
11.
11? Close.
Yeah.
Oh.
This is like an acidic environment. And what if I had a base environment? Like I increase this to 1/100th of a molar.
You're gonna have to do 10 to the minus 12.
Perfect. Because they have to equal to the constant. And this is what happens when you shift. And how much of this is used up? This much between this and 10 to the minus 7 and this is used up, which means none is used up. Not in comparison. If you have $1 billion, I give you $5, you have $1 billion. You don't have $1.5 billion. Because you probably didn't have $1.000 to begin with. Okay, if you put this on a scale, that means I gotta have 100th all the way to 10, like to the 0.0000000000001. If I scale this, it would be all the way down to Talia's house and around the corner and half from Chick-fil-A, Los Angeles West Campus, everything else. So we can't put this on a scale, so we have to use a log scale. The log of this is minus 7, this is minus 7. The log of this is minus 11, minus 3, and minus 12, and minus 2. I don't like these. Why do I not like these?
Is it negative?
Because they're all negative. Because almost everything you get is less than 1. So we're going to not use a log scale, we're going to use a negative log scale. And the negative log of 10 to the minus 7 is 7, this is 11, this is 3, this is 12, and this is 2. Now, which is bigger?
The H.
10 to the minus 3 is way bigger or less small.
Yeah.
Therefore, in the p scale, in the negative log scale, which is bigger, 3 or 11?
3.
3. How much bigger is it?
Bigger.
10 to the 8th.
10 to the 8. Yeah.
Because these are log scales. So you find the difference. What's math for that?
Subtract.
Okay, so what's 11 minus 3?
8.
8. We know which one's bigger?
3.
3. And how many times bigger? It's the difference, which is 8. 10 to the power of 8. So a lot bigger.
Is this where pH comes from?
pH.
And that's why it's equal at 7.
P means negative log.
Yeah.
H means molarity of the H plus ion concentration. That's what pH means. It is not an arbitrary scale of 0 to 14, with 7 being neutral. 7 is neutral not because of arbitrary scale, because on its own, water will dissociate to 1 millionth of a molar on its own, and the negative log of 10 to the minus 7 is 7. So we do this thing called Payne square. Y'all do this with Perry.
Yeah, we did.
So SL probably didn't do any of this stuff.
We did not.
So a solution sitting there by itself, not doing anything, is related in 4 ways. So this is not
Yes.
mixing solutions. This is just a resting solution. It could be pure water. It could be an acid. It could be a base. This is not changing. This is not 2 different things. This is one thing. And we can do this. What does square brackets mean?
Concentration.
Molar concentrations, right? So if you are looking at this guy right here, we know that if this is 10 to the minus 11, this is 10 to the minus 3, and we get that by saying kW divided by OH minus equals H plus, correct? Or if we're going this way, we would have kW divided by H plus to equal OH minus. Either way, it is kW divided by the concentration of one to equal to the concentration of the other one. Whichever way you want to go. What will kW be all the time?
10 to the minus 14.
10 to the minus 14. Unless they tell you, I have changed the temperature and now this is what happened and that kind of stuff. And it'll be a Le Chatelier's problem essentially. But otherwise, it's always this. How do we go from 10 to the minus 3 to 3?
-1.
Negative log. So go from here to here. This is the molar concentration. This is the negative log of the molar concentration. So going down, you take the negative log of the molar concentration. And going down, you take the negative log of the molar concentration. Why this side? If you have a base, we're going to know the concentration of the hydroxide. And we want to get the pH. We don't have a pOH scale for base and a pH scale for acids. We just have the one scale.
Yeah.
So you can either go down and over and down and over will be easier, but you can go over and down. What does pOH stand for?
It's log of M
It is the
negative
negative log of the molarity
yeah.
of the hydroxide ion.
So
All right.
For the top part, is that going either way?
Yeah.
Okay.
Yeah, so if I wanted hydroxide and I knew the hydrogen ion, I could put the hydrogen ion here and that's hydroxide. If I wanted the hydrogen ion, I knew the hydroxide, put the hydroxide here, because either way, if you want this, you put this down. If you want this, you put this down. So it works the same way. That's why I didn't write in OH minus or H plus, because you can't go either way. And either way you go, the KW's on top. So that makes it easy. So going down is the same thing, same math operations. If it's a whole number, you should be able to figure out in your head. If it's not a whole number, I hope you bring your calculator, unlike my sophomores, who had a test that had math questions on it, and like 6 people came in with that calculator. They're like,
What'd they do?
they went and borrowed one. They know not to ask me for mine.
I learned my lesson the first quiz.
I mean, it's good to learn lessons. Okay, going across, this is the easiest one. How are 3 and 11 related? How are 12 and 2 related? How are 7 and 7
They
related?
equal 14.
They add to be 14. So if these add to be 14,
Minus 14.
then 14 minus 1 equals the other one. So we're going to have 14 minus POH equals pH. I say it that way because typically we're going to pH and therefore you're going from POH. But I could figure out POH by saying 14 minus pH equals that.
Is it always 14?
Yes. Because, what is the negative log of KW? Also, when you calculate this, did you really multiply them in your head?
No.
What'd you do?
Added on the.
You added
The negative log.
the exponents,
Yeah.
right? The negative log. So what are we doing down here? We're adding the exponents.
So
If
So it's the same thing, it just looks a lot cleaner because it's already negative logs.
I was just gonna ask, so 14 minus pH is POH also?
Yes,
if
we just typically don't go that way, but we certainly can. So 14 minus pH equals POH.
right.
Just like this guy, and I'm sorry, Harry, just like this guy, this could be H plus in the bottom to get OH, we OH in the bottom to get H. Now,
Okay, so if it's not standard conditions, would pH max?
this would still work, but it wouldn't be 14.
Yeah. it
We would need to take the negative log of this and put it down there. But you're never going to do that. But you're right, that is the thing. Okay, going up. Is there a time in which you have the pH and you need to figure out the concentration of the hydroxide or hydrogen ion concentration? Yes. So we need to do that. So the bottom is already the negative log. So we have to undo the log and we have to undo the negative. There's probably several ways to do this. But in your calculator, this is how I punch it in. I push second, log, negative, P number. So like if you go from POH up or pH and up, you punch this in. So do me a favor. Punch in 11 in your calculator. Type in 11. And then I want you to punch in second log negative 11 and see if you get 10 to minus 11.
You gotta get it down here.
I got it.
If you have like a TI-30, I think the order of operation is different. So you gotta be careful. So, yeah, you got it or no?
It's second.
Second log,
Yeah.
like regular log, not LN, like L or G. Then negative,
Yeah.
and then whatever the P number is, that's at 11, so you get 10 to minus 11.
Yeah, you get either.
I got 1.1 times something, I got 10.
1.1? You start off with,
11, 10 to the negative 11. Oh wait.
let me see.
You're getting this in order.
Whatever the
But second log,
Yeah.
negative 11.
Oh,
You got this?
Oh,
That's
yeah.
just the
You
sample
got
number
this?
he said to put. You see it says.
Oh, clear
No, I
it.
haven't.
Or you could just write it.
Yeah, and so it's nice to be able to do this with whole numbers, because what I used to do when I was in college, because I wasn't that smart, I used to figure out how to do it with simple numbers, and then if you use complicated numbers, it works the same way. So if you can go 3, 11, 10 to minus 11, 10 to minus 3, 3, like that with simple numbers, then you can figure out the correct way to punch in a calculator if you have like 2.35, and then everything else is really complicated than that. Claire? You're gonna put log maybe negative 11. Yep. Shift log negative 11. And that works. Okay, this is the pH scale. If you throw in something that functions like an acid, it will be producing this, and you'll end up with a molarity of this somehow, some way. If you put in something that functions like a base, then you're going to be producing hydroxide ions, you sort of here. The question typically is this. So if it's an acid, you go down. If it's a base, you go down and over. You could go over and down, but subtracting from 14 is really simple. If you have a strong acid, okay? If you have a strong acid, like you have 0.04 molar HCl, how do I know this is a strong acid?
Just one of those.
It's one of the 6. How much of it falls apart?
All of it.
All of it. What is the molarity of the chloride ion? I don't care. But what is the molarity of the hydrogen ion?
0.
0.04.
Oh, right.
So you're saying the molarity of the hydrogen ion is 0.04.
Okay. Yes.
Yeah.
Yeah.
Then you're on the pink square. You get that number, negative log, you got pH. If you had ammonium hydroxide and you had 0.04, This thing falls apart completely. Falls apart to the sodium ion, which I don't care about. And it falls apart to the hydroxide ion. How much hydroxide ion do I have?
0.04.
Because this is a strong base.
Yeah.
So how much of it falls apart?
Oh, all of it.
All of it. And therefore I end up with 0.04 molar of the hydroxide ion.
Yeah.
So if I figure out the molarity of a strong base, I'm on the Payne square,
Yeah.
negative log 14 minus. If I have a strong acid, I'm on the Payne square, figure out molarity. How can I make this a little more complicated? I give you grams and milliliters.
You can convert to liters.
Right, those are liters. So these are molarities. Now, the thing we're not at yet, and we're not gonna get there because we got like 30 seconds. If it's a weak acid, we have to go through an equilibrium to figure this out. And then once we go through an equilibrium to figure this out, then we're on the Payne square and we go down, or for a base, then we're on the Payne square and we go down and over. That's the part we need to add. But to do the math, like to understand what we have and what we should be calculating, we need to learn all the stuff we learned earlier, which is not math based. If I give you HF, that's a weak acid. If I give you F minus, that's a weak base. If I give you ammonia, that's a weak base. If I give you ammonium ion, that's the opposite, and therefore it's a weak acid. And then the thing we have to add to this is that when we have things that are so weak, they're weaker than water is, and which means they don't do anything, and that can be as confusing as anything. It's a disregard stuff that's there. And so that's what we got. So do your best on the homework. If you got some problems that we haven't touched, you don't have to do them. I think you should be able to work through a lot of it. Subscribe, hit the button. You get the recipe if you
Nope.